Thank you, Yannick. And I'm just using this opportunity to, I give my talk, to make a quick announcement about an event which I think is interesting for many people here in this audience. So it's a research school happening in Marseille, at the CIRM, if you know this place. It's going to be next December, so you see first week of December. It's called Beyond Permutahedra and Associahedra. It's organized by César Ceballos, who was here earlier this week, and also Vincent Pilot, Ivan Raskin, and myself. And if you look at so we don't have a precise schedule or planning yet, but you can see that there will be 2 mini courses, one given by Nathan Reading, who is here, and the other given by Martha Yip of University of Kentucky. Here you have the list of invited speakers. This include especially Christian Stumpf, who was here, he's here also this week, and Bérénice Delcroix-Auger, Eleonore Faber, Thorsten Mütz, and Frédéric Patras. So the topics are very close to, even though it's not centered around non-crossing partitions, it's really close to some things that have been discussed this week, especially, for example, free partitions also going to be mentioned. The free probabilities are also going to be mentioned. There are many things. Also, it's really it's going to be a really good place to go for master students and PhD students. We'll make a focus there for the young generation, so that they could understand all these problems, and also they will have opportunity to give talks, present posters. We have some funding, so we can pay for especially for the stay at CIRM. So if you can fund, for example, for your own tickets, then the stay can be covered. And also there is a whole semester before that in Barcelona on similar topics organized by Vincent Pilot and Arnaud Padrol. So if you have like some free time at the next fall, if you want to spend a whole time meeting great people and talking about interesting subjects in Spain and then in south of France, well, please come. So you will find this event on the CIRM program page. You can already pre-register, which is some kind of application for the event, and we will give a date and everything a bit later. And we will send announcements also soon reminding you of all this and sending the website. So, okay, so thank you for this. Now I'm going to move to my talk. So first I want to thank the organizers for inviting me to give this talk. One thing I should say is that even though non-crossing partitions are an object really close to my work, I've never worked directly on non-crossing partitions. And one consequence of that is that my talk is not about non-crossing partitions. So you should know that. But I've chosen a subject which I think is going to interest many people here, because it relies on things that people here are like to work on, especially Coxeter groups, and also descents, inversions, notions that many people here are familiar with. And it contains an open conjecture. So it's a win-win situation, because you want to hear my talk and you want to solve the conjecture. So there is some work for you. But for me, it's a win, because you're going to get interested in my work trying to solve my conjecture. So see, it works. And I'm leaving tomorrow, but I will be here this morning and this afternoon if you want to discuss further or on this topic or other topics that I work on. So it's a conjecture on descent invariant in the weak order, and it's a joint work with Christophe Holbeg from UQAM. So I'm going to start with, we start with the Coxeter group. Okay, so this is something you're all familiar with. And we're going to take an element and to look at the inversion set. So, I'm talking about the left inversion set. So it's a set of reflections such that when you multiply your element to the left, sorry, I was kind of invading the space. when you multiply to the left, you reduce the length. And here I'm talking about the usual length of permutations in terms of simple transposition. So everything I'm going to say is going to be for every Coxeter group, but I'm going to give all my examples in type A. So now we're going to do an example in type A so that we're all clear what we're talking about. So this is an element of a Coxeter group in type A, so it's just a permutation. And these are the list of all possible reflections. And what I'm talking about when I say inversion set, left inversion set, I'm looking at two letters in my permutation, which are in the wrong order. So you see you have the 5, which is before the 2, and it means that this permutation has the inversion 2, 5. So because we're talking about left inversions in type A, it means we're talking about inversions in terms of values. So here it's 5, 2, 2, 5, okay? So for example, 5, 3 is also in the wrong order. So we have 3, 5, 4, 5, etc. Let's select all the inversion there. And this is an inversion set, okay? Up to there, I think everyone can follow. So you know also that this inversion set need to follow some rules. So for example, they need to be transitive. So if I have 1, 2, 2, 5, I also need to have 1, 5. And you need to have the non-inversions to be also transitive. So for example, here I have 3, 5. I need to have either 3, 4 or 4, 5. Okay, and so these rules, I've told them in type A, but they exist for all Coxeter groups. Okay, so in certain cases, you can split the set into two different inversion sets, such that each of them is still a proper inversion set. Okay, so here what it means is I have my W here, but I have also a U and a V, such that the inversions of W are exactly the disjoint union of the inversions of U and V, okay? So this, we're going to call that a bipartition of, yeah. No, yeah, wait. No, it's not exact, no, if you take the, it's something a little bit different. I'm going to show it right after. No, but it has a translation. I'm going to show it right away. So you can see that in the weak order. So that's why there was weak order in my title. So the weak order, we've seen it in the class of Emily Barnard, and it's going to, well, I'm going to show something of it here. So the weak order, we order the elements of the group by inclusion of inversion sets. So the inversions we've just seen. So here is the interval between the identity and W. And because this is by inclusion of inversion, U and V are inside this interval, okay? And you have that the join of U and V is given by W, because because W contains exactly the inversions of U and V. And the meet is going to be the identity because they have no inversion in common. Be careful though that the join in the weak order is usually not just the union of the inversions. This is a special case here, that the union of the inversion give directly the inversion of another permutation. Usually you have to make a closure there. You have to add some extra inversions, a transitive closure. So in this case, we're in a specific case where you don't have to do the transitive closure, and you didn't have any inversion in common. So it's particular. It gives you something for the weak order, that if you look at the distance between the identity and W, so this is the number of steps you have to do in the weak order, so it's the length of W. You can find the same distance here between U and V, because you're going to add all the inversions from U to W, and then you can remove all the inversions of U and go back to V. So this is like the shortest path in the graph between U and V would be to go up to W and back to V, or to go to the identity and back to V, that will work as well. And we have this thing that if UV is a bipartition of W, then the distance between U and V is exactly the distance between the identity and W. This is also the maximal distance in, if you look at this graph, the interval here, if you forget that it's an order, you just look at the graph and you at the maximal distance between 2 points. This is the maximal distance. So it's called diameter of this interval. And here we have a case where you have two diameters. So we say that it's a rectangle. And it's not always the case that you have that. It's actually not so common for an element W to have such a bipartition. So here are the numbers that you find if you try to look at, okay, what are the elements W, which I can cut into this two parts. And so I've put two lists of numbers, the ones which admit a bipartition and the ones which would call partition indecomposable. So if you sum, you find the factorial. Okay, so I have my numbers are consistent. And you see that they are weird numbers, okay, that they might not have like a nice formula because, okay, it's difficult to find anything. So it's good for me because I was not interested in looking at those numbers, but it was just for you to see that they are, and they're actually not in the OAIS, and I plan to add them, but I haven't done it yet. No, it's not unique, the decomposition. You can have none, you can have one, you can have many. It's not unique, no. Okay. You can yeah actually. Yeah, you could extend it. I haven't looked at it yet. In the paper we don't do that, but we give the polynomial of this number up to the length of W also, so that it gives you different approach. So why am I interested in those bipartition? So why are we interested in those? So they appear in a geometric problem from Belkin and Kumar in 2006. So eigenvalue problem, new product cohomology of flag varieties. And I'm not going to tell you more about that because I don't know more about that. It's just to tell you that there are some people who think this problem is important and do very difficult things with it in algebraic geometry, but I'm not those people. And so, but there are other people who found it interesting also in terms of more enumerating algebraic in algebraic statistics, or they also appear in the Littlewood Richardson cone. So here are two other papers there. And now I'm going to tell you why I have been looking at them. So there is my motivation is a conjecture that was formulated by Resire on the number of descents. So now we're going to move to the descents. So I'm going to just define quickly that we're going to look at the right descents of an element. So now we take a simple reflection and we multiply it to the right, and we wanted to reduce the length. So that was a general definition for Coxeter groups. What does it mean in type A? A simple reflection in type A is a simple transposition. So a transposition between two consecutive values. And the fact that we multiply it to the right means we apply it to the position. So here, 1 and 2, it's first position, second position. And the fact that it decreased the length meant that the first position was, the value was higher than the second position. So a right descent in type A is just a normal descent in the permutation. You read the permutation, 5, 2, it descends, 6, 3, it descends, 4, 1. Okay, so this one has 3 descents, which I've marked here with a dot. Okay, 3 descents. Okay, and what is the conjecture? Oh, before that, the descents, they also have an interpretation in the weak order. So they are just what we call the co-atoms of W. They are the elements just before W in the weak order, which are covered by W. Okay. So now, what is the conjecture? The conjecture is that when you have a bipartition of W, then the number of descents of W is the number of descents of U plus the number of descents of V. So here is an example. This is my previous W. It has 3 descents. Here were my U and V that I showed you earlier. Here's the 1 descent, 2 descents, 1 plus 2 equals 3. It works. Okay. It looks extremely simple. So it's a bit frustrating because you're like, that is so easy, but it's not trivial. So if you have to be careful, because if you, for example, if you look at left descents, then it becomes trivial. So it looks like a trivial problem, but it turns out it is not. And how did I hear about this problem? So just before that, this is what it means in the weak order. You would have W, and the descents of W, and you would have U and V, and the co-atoms of U and V would add for, and the sum would give the co-atoms of W. Yeah? Yeah, sure. No, I didn't say that. I say for the left, if you go at the sum of the left descents, so if you take both left inversions and left descents, I don't remember what was the argument here, but for example, it's trivial that the number of atoms of W is the sum of the atoms of U and V, because there is just, if you want to start from the identity, if you want to go to W, there is just one way. You can either go through U or through V. You don't have a choice. Okay? So I didn't know this conjecture. I heard it in 2022 when I was in Montreal, and it was presented by Christophe Olveg at the seminar. And I'm not a Coxeter group person, but when he presented it in 2022, it was completely open still. It had no proof, even in type A. And I'm a type A person. So when he showed that, and he said the sum of this, the inversion thing, and then the sum of descents, I was like, okay, it's not possible that we don't have a proof in type A for that. I mean, it's inversions, descents, come on. We have to find something out. So I did think of it, and I actually got it was not trivial, but after a few weeks, I got it together in 2022. But we took some time. We tried to generalize it to all Coxeter groups, which we couldn't do. And we took some time. And in the meantime, there was this paper of Resaya and Francon, who proved it for all Weil groups. So it includes type A. But thankfully for us, they don't have a nice proof for type A. They have a proof that uses algebraic geometry, complicated tools, and I didn't read the paper, but Christophe Olveg looked at it, and he told me it's like 20 pages of things, of case-by-case proof for all crystallographic Coxeter groups, very complicated to follow. So, yeah. Yeah, so that was, yeah, exactly, also infinite. So there is this, so we know that it's true for Weil groups. In our paper with Olveg, we give a direct elementary proof for type A and B. So when I say elementary, I don't mean that it's a trivial proof. I mean that it uses only very simple tools. Like, you don't even have to have properties of the Coxeter groups. If you know what are permutations and inversions and stuff, you can prove the whole thing. You don't even have to understand the whole picture to do it, which is actually why I did it. Oh, sorry, yeah. I wrote my slides between Paris and Stuttgart, and then when I was sleep deprived, so you can, there might be, so if it's my only typo, I'm glad. So this is what I'm going this is what we did, and this is the part that is interesting for you, is that even though there were these two work, it's still open for all Coxeter groups. So not only all finite Coxeter groups, but all infinite Coxeter groups as well. So the computation that we've made, and especially Christoph Olveg has made on different Coxeter groups, let us believe that it is. And what I hope is that the proof that I'm making in type A and B, someone who understands Coxeter groups could try to see how it could be generalized, because I think there is a good idea in it. But it's not an easy one, because we tried and we couldn't find how to generalize it to all Coxeter groups. So I'm going to show you the proof in type A, because it turned out that it's a very, once you have the right construction, it's extremely easy. This is why I like this proof a lot, because I find it completely clear and it makes the paper, for example, very easy to read. So the idea is to do it recursively, and we're going to find a decomposition of our element W. So how do we cut W into two parts? We look at the 6 here, and we say that everything that is left is called a left letter. Everything that is right is called a right letter. And so here in red and blue, so there are the red letters and blue letters, and we make, and we select the left and blue, the right and blue, either I should say left and right or red and blue. The red and blue letters in U and V is 5 and 2, 5 and 2, okay? And now I just make words keeping all just the letters of the same color. So I just, so in W, it's easy. It's just you cut it right in the middle. You keep what is right, what is left. In U and V, the letters are kind of mixed together, but they have a very nice property, is that the descents here are always between two letters of the same color. And that's the key point. And not only that, but when you join the colors together, they don't create another descent. So these letters tell you all you have to know about the descents. You can separate them, and you will still keep your descents where they were, basically. Okay, so here, for example, 5, 2, here the descent 5, 2, 6, 1 is here, 6, 3 here. So you have split the descents between the red and the blues. So what it means is that here, the left word, they form a bipartition, and the right words, they also form a right partition, but of a smaller group. So if you're a type A person, the fact that you have letters that are not 1 to n, it doesn't bother you. But if you're a Coxeter person, like Christoph Olveg, he tells me, but these are not permutations, look. They have like a bunch of other letters. And because I'm a type A person, I'm like, this doesn't matter. We standardize and keep the descents untouched. So this is one of the things here that is very easy to say in type A, but this kind of cutting and mixing the letters and stuff is exactly what is not so easy to generalize it in a way that works for Coxeter group. Yeah. It's here. It's just because you choose the 6, the maximal letter. Right. You look where it is, and everything that is to the right is blue, and everything that is to the left. So it's W which decides which is red and which is blue, and tells it to U and V. Okay? And so now we're almost done, because we had a problem, and we cut it into 2 smaller problems. So as a computer scientist, I'm happy. And as a mathematician also, because you can make a proof by induction doing that. Except I have a problem here, is that now I have the right words, and the maximal letters is 4 and is here. So I cannot cut it into 2 smaller problems. But here I have another idea, which is, I don't like this 4, I'm going to remove it. So I just remove the 4, I call it the decreased right word. And in W, the 4 is going to be the first letter by definition. So when I remove it, I remove a descent, except if it was just 1 letter, which is a trivial case. So if I have more than 1 letter, I remove this 4, I'm removing a descent. And it turns out that you can prove and there is some proof here, it's not trivial, that in U and V, when you remove the 4, you see that here you remove the 4 and the 4 is inside a descent, so the descent is kept. Was here, the 4 is inside an ascent, so when you remove the 4, you lose the descent. So you lose exactly one descent between U and V, which corresponds to the descents that you lost here in W. So it works. And this is not trivial, but this is an elementary proof in the sense that it depends on the properties of the bipartitions and the inversions. And if you put this letter there, then you have to put this letter there, and all the details like that. Okay, so that works. And we have a proof for type A. So this is what I did in 2022. And then we spent some time trying to understand this decomposition here and see if we could find a way to have it general for all Coxeter groups. This we couldn't do, and we were also, I left Canada, I had other things in mind, and so it took some time, and at some point I met with Olveg again, and he said, okay, let's just finish this paper the way it is. Could we do type B? And I'm like, yeah, sure, type B must be almost the same. And I was right, so I took a few weeks and I did type B also. So in type B, this is exactly the same idea. It's just that you have to be a bit clever about how you cut your word. But so a permutation in type B is a permutation of the, so now if you're in the Bn, you're going to have a permutation from minus n to plus n. So here I put a bar on the numbers where they are negatives. And it's symmetric in the middle, so the left part is just the right part, but with minus instead of plus, okay? So you can actually look at only, you could actually look at only this part to identify your element, but because of the construction, it's better to have the whole element outside. And you do basically the same. You take the maximal letters, you cut it here, and you end up with something of type A, which is what is right of your letter, and something of type B, which is what is in the middle of 6 and minus 6 here. It turns out that you don't have to worry about the case where where it's a minus 6 on the right, because there is a Coxeter thing that tells you that is going to be the same. This is the part where you use the Coxeter, some properties of the Coxeter groups to prove that, but you can also do it directly. I had also worked out a decomposition when the 6 was negative here. So, but this was just for information. In general, you can just keep to the fact that 6 is positive. You have a left word and right words, and they will have the same nice property that the descents are going to be always between letters of the same color, and so you're able to cut them into two. One is a bipartition of type B of a smaller type, and one is a bipartition of type A, and you've already proved that it works. And because you're in type B, it's also still easy to do standardization. So here you standardize, then you have exactly two bipartitions of smaller size. You don't even have to worry about the case of the maximal letter and empty left word, because there you have a type A and type B, and so you've already proved things to be true for type A. And that's it, it works, and also in type B. And so it gives us two elementary proofs for type A and type B. And the conjecture is, how do we make it for all Coxeter groups? So just think a bit in terms of Coxeter groups to understand what we did in type A and B. We found a way to cut, you look at the diagram, we found a way to just cut somewhere in the diagram that makes sense and give a decomposition that is that's not a classical Coxeter decomposition. It's not a coset. It's something a bit more elaborate than this. But we found a way to cut it and to decompose it into two elements which kept all the information that we were interested in two smaller groups. And that's how we proved it. But we couldn't find how to cut a general Coxeter diagram like this into two parts doing this thing. Basically what we miss is in type A and B, I do. The maximal letter is N. I'm just going to find the N and cut things there. And it worked. But I don't know what is this maximal letter for all the Coxeter groups. See, that doesn't make sense when you leave the type A, type B world. So the goal is to find a group generic recursive decomposition of element that keeps the descent the way it does in type A and B. So here, this is now your work, because I did my part. I did type A and B. So, okay, and I'm going to stop here. So thank you very much. And the paper is on the archive since December. So if you want to look at the details, it's all there. By partition? Well, there is it's the only thing we could say was it's the rectangle thing, that it's an interval where the diameter that has many diameters, like more than one. Like any element has at least one diameter, and it corresponds to one bipartition. So it has basically any bipartition gives you a diameter. So if it has only one diameter, it has only one bipartition, which is the trivial one, so you're not interested in it. And if it has other bipartitions, it gives you other diameters. So on a graph perspective, it has a meaning, like it's the thing that you have different elements that are of maximal distances. But I don't know if they have other, like in terms of posets, I don't know if they have properties, specific properties. I haven't looked at it, so we should, this is a question I haven't thought of about. Yeah, maybe, I don't know. Yeah, I haven't looked at it this way. Yeah, I mean, actually, if you prove it for bipartition, it proves it for any partitions in more. So the original conjecture in the first paper, like the geometric question, I think it was about 3 partitions specifically. And one thing we write explicitly in the paper is that if you prove for 2 partitions, for bipartitions, you prove it for anything more. So if you have a partitions into more, the sum of the descents of the element is just the sum of descents of the other element. I don't think so. I haven't looked at it. I have looked very little at the enumeration. I just realized when I was preparing the slide that it was not on the OAIS, and I sent an email to Olveg yesterday saying, oh, it's not? Have you thought of adding them? He said, no, you should do it. Yeah. I've tried when I was trying to generalize it, I tried to do that, and it's not easy. I couldn't come up with something, but I kind of remember that there is some. So the part that I was trying to look at is the decreased part. So the part where you have a maximal thing. I mean, it's yeah, in here, for example, so the right part, no, it's not, you don't, we don't have it here. I didn't, it would be interesting to look at the right word, but I couldn't see anything, looking directly at this diagram, I couldn't see a way that would make sense to cut it in a clever way. haven't tried type D. I've tried type A and type B, and then I decided that if someone, my guess would be that type D is possible. That if you, but it's just that I had done already A and B, and I was like, okay, let someone else look at type D or try to find the generic proof for all Coxeter groups. But if you have a student and you want to have them work a little bit, you could give them type D to see if it makes sense. I is it even possible? No, because it has to. It has. It's the same if you look at um, because if, the interval in the you will they will have the same. Oh no, you're right. It would be the same if you looked at the recalls and so I don't know. In my head it should work both for W and W inverse, but I might say something wrong. We in the paper we kind of cover all this case of you can multiply it by the maximal element. There are a few things that you can do and you keep the property, but I don't remember exactly what they were